Hi, I'm Alejandro Sanchez.
I'm Jose Trinidad Gomez.
I'm Pellegrini,
I'm Nathalie Ortiz.
and this is our senior project presentation in which we created a cell layout for the Cast-Rite Corporation.
First and foremost, for our project, we'd like to address what was accomplished. Using a heuristic approach, we were able to develop an optimized cell layout for an automated die casting process, which resulted in a reduction of 74% in cycle time over the current state, a 634% increase in daily throughput, which now far exceeds the required production rate, and a decrease of 67% in labor cost over a 5-year analysis period. Throughout this presentation, we will go over the company background, followed by a description of our project and an analysis of our current state. Then we will review our hypothesized alternatives, which will be summarized, and finally, we will conclude with our recommendation for the company.
The company we chose to work for is Cast-Rite Corporation, located in Gardena, California. They are a die-casting company founded in 1941, which produces small to medium-sized aluminum and zinc products, which can be found in an array of industries, including marine, aerospace, automotive, and electronics.
For our project, we were tasked by Cast-Rite to create an optimized automated cell layout centered around a new automated die casting machine. The machine was to be used to produce a part under contract at a production rate of 800 parts per week for 5 years. The purpose of creating the cell layout was to help the company reach their required production rate and reduce their overall tack time, with the goal of also reducing their production costs moving forward. We believe we would be able to solve this issue and help the company in reaching these goals by analyzing their current state and current process to help in the creation of a more streamlined cell that would not compromise standards or quality. Currently, Cast-Rite has a contract with a well-known marine manufacturing company to manufacture a motor mount at a rate of 800 parts per week, meaning that their tack time must be 6 minutes, as the part is run for 2 8-hour shifts. In their current state, their cycle time is around 36.56 minutes, with a bottleneck occurring at the machining operation, which takes 24 minutes. With this information, we determined that in the development of an optimized cell layout, their machining capability would be the central focus in our efforts to help them meet the required production rate.
These measurements were taken from time studies we performed at Cast-Rite to establish a baseline for our project and gain an understanding on the process. Here you can see the cycle times for the automated die casting portion of the process broken up into its main operations. As you can see here, the longest cycle time is the prepping and the shot of the die casting process, which actually runs simultaneously with the other operations listed. Here you can see the next operations following the die casting cycle. As you can see here, the cycle time for every operation falls below 4 minutes, except for our machining process, which has a total cycle time of 24 minutes, making it our bottleneck by a great amount.
The current state has 2 shifts and utilizes only 1 CNC machine. We found that the total processing time for the current state is around 33.5 minutes. We will try to reduce the processing time in order to meet the daily demand of 160 parts.
Our current state layout shows that shortly after the first inspection, the parts are then transported over 250 feet to another building for the next step in the process, hauling such a heavy load, taking 2.37 minutes, which is already 1/3 of the cycle of our target cycle time. This spaghetti diagram shows the approximate path the entire cycle takes.
As you can see from the graph of the cycle times of machines and other operations shown above, the machining process has the highest cycle time while the other operations are relatively low, showing that clearly something must be done in order to balance this process.
Using the data we collected from this facility and inputting it into ProModel, we can see that the average part time spent in the system is 454 minutes, and the total time the part is being operated on is 33.41 minutes. This means that during 2 8-hour shifts, their daily production rate is only 38 parts, falling very short of their production rate requirements. This is due largely to the blockages occurring at their machining center, as they have only 1 CNC machine they can use for production. This data will also be used to establish a baseline for which other alternatives would be compared. Using the knowledge and familiarization we gained with their process and equipment, we were able to formulate 3 alternatives to their current state using heuristic approaches. The first being the purchasing an additional CNC machine and adding an extra shift to meet the required production rate by modifying their tack time. The second alternative is to add 2 additional CNC machines to their shop, but keeping the same number of shifts and thus the same tack time. Our third alternative is implementing a specialized machine developed by the company, which they refer to as a shuttle machine, and reducing the number of shifts to just one. For our first alternative, we considered adding one additional CNC machine to the cell layout. As they have only one CNC machine currently capable of operating on the part in question, the additional unit would have to be purchased and could be acquired for around $90,000 secondhand. Also, in order for them to reach their required production output, they would have to run 3 8-hour shifts a day for 5 days a week, and they do not operate on weekends. By implementing this additional machine and extra shift into our simulation, we were able to start to see minor improvements with a reduction of 72.94 minutes in which the part spends in the system. The cycle time as a whole was reduced by 32.82%, and daily part production was increased to 162 parts per day, surpassing the required production rate.
In the first alternative, we increased the number of CNCs as well as the number of work shifts from the current state. We also included both CNCs into the work cell, and by doing this, we reduced the travel time from the die casting process to machining. These changes allowed for our total processing time to be reduced to around 21.5 minutes.
The second spaghetti diagram shows our first alternative and the new layout condensed into the space available within the same building. The CNC machines will be situated where the part exits from the die casting machine and will follow the new path shown for the preceding steps in the cycle. The travel distance is drastically reduced along with worker fatigue.
With the addition of a CNC machine, the average cycle time per part for the machining process will be reduced by 50%. But as you can see here, the machining process still has a relatively larger cycle time compared to other operations. By assuming a standard labor rate of $31 per hour and the purchase of a used CNC machine for around $90,000, we're able to perform an economic analysis to determine the future cost for the additional machine and the labor required to operate it. By assuming an interest rate of 10% per year for both the machine and the labor and an initial investment of $90,000 with 3 operators, we determined that the future worth cost in 5 years would be just over $3.5 million.
For our second alternative, we considered adding 2 additional CNC machines into the cell layout, which could be purchased at $90,000 each or $180,000 in total secondhand. Due to them having a total of 3 CNC machines at their disposal, they could continue to only run 2 shifts per day, which would have a dramatic result on their labor costs. By implementing the additional machine and extra shift into our simulation, we were able to start to see minor improvements with a reduction of 119 minutes over their current state in which the part spends in the system. The cycle time as a whole was reduced by 44%, and daily production rate was increased to 161 parts per day, again surpassing the required production rate.
For our second alternative, there are in total 3 CNC machines. The number of shifts will be kept the same as the current state at 2 shifts. For this scenario, the total processing time was around 17.5 minutes.
This spaghetti diagram shows our second alternative and how the third machino would fit within the cell. This third machino allows the 3 workers to man their own station and increase utilization. Although the fit would be more snug, it is possible to fit 3 machines of this size into the allowed space.
With the addition of 2 CNC machines, the average cycle time per part for the machining process will be reduced from 24 minutes to 8 minutes. This will create a smoother flow of parts and as a result, lead to a decrease in shifts required to meet the desired production. By again using a standard labor rate of $31 per hour and the cost of 2 used CNCs for $90,000 each, we're able to perform an economic analysis to determine the future cost for the additional machine and the labor required to operate it. By assuming an interest rate of 10% per year for both the machine and the labor, and an initial investment of $180,000 as well as 3 operators, we determined that the future worth cost in 5 years would be $2.5 million.
For our third alternative, we discussed the creation and implementation of a specialized machine dedicated solely to the production of the contracted part with the company. Shortly after, they deemed this the most prudent option and thus began working on it. After several discussions with the engineer heading the creation of this machine, which they refer to as the shuttle machine, we were informed that the cycle time for their machining operation would be reduced to just 1.5 minutes. This was accomplished by using multiple spindles simultaneously to perform all the required operations, resulting in this new, drastically diminished operation time. The overall cost for the development of the machine was estimated to be around $150,000 as it required specialty and often bespoke equipment. After implementing the shuttle machine into our model, we were able to see drastic improvements over their current state. These improvements included the part spending only 11.57 minutes in the system, which is a reduction of 97.45% over their current state. Their cycle time was now only 8.75 minutes, which was only 26.32% of their current cycle time, and a daily throughput of 241 parts per day.
For the third alternative, we included the specialized machine and reduced the number of shifts to 1. The specialized machine has a total cycle time of 1.5 minutes, which greatly improved the total processing time to around 11 minutes. This is a significant reduction, which will meet the daily production rate of 160 parts.
Our final alternative shows how the specialized machine would condense the travel time to nearly insignificant and free up room within the immediate cell. This space that was created by eliminating the need for the CNCs can very well be used for storage.
Once again, as you can see from the graph of the cycle times of machines and other operations shown above, cycle times are now relatively more balanced, with every operation falling under 4 minutes. With the implementation of the specialized machine, the machining process no longer has the highest cycle time, falling from the current state of 24 minutes to approximately 1.6 minutes. By again using a standard labor rate of $31 per hour and the cost of developing the shuttle machine for $150,000, we were able to perform an economic analysis to determine the future costs for the additional machine and the labor required to operate it. By assuming an interest rate of 10% per year for both the machine and the labor and the initial investment of $150,000, we determined that the future worth cost in 5 years would be just under $1 million. As you can see with this alternative, the number of shifts is reduced to just 1 shift with only 2 workers required in order to produce the required production rate.
When comparing the 3 alternatives economically, it can be seen why the third alternative is the superior alternative, as it comes to just 1/3 of the one-third of the cost of the first alternative and less than half of the cost of the second alternative, coming in at just over $998,000 for a 5-year analysis period. In this graph, you can see the improvements made by each alternative in terms of the percentage in which each scenario is compared to the current state. As can be seen, the current state was used as a baseline for these comparisons, represented by the light blue. The metrics we used for our comparisons were the amount of time that the part spends in the system, followed by the amount of time it's being operated on, and finally the overall cycle time. Clearly, the third alternative is once again the most prudent option, as it greatly reduces time in which all measures were used. This graph is a comparison of the overall daily production rate. Using the current production rate of 38 parts per day as the baseline, followed by alternatives 1 and 2 producing 162 and 161 parts respectively. Finally, far superseding all other alternatives is the third alternative, which is capable of producing 241 parts per day, a drastic increase over their current state. After conducting our analysis, it is apparent which alternative provides the most benefits for the company moving forward. Needless to say, our final recommendation would be the implementation of the specialized shuttle machine within the cell. This is based upon the drastic improvements we touched upon in our previous slides, such as the reduction in cycle time and considerable reduction in labor costs. As such, we've chosen it for our final recommendation. Thank you.